Hello guys, for today's video we will check and implement the following paper. It's quite recent, it's from 2025, and well, the name of the paper is Fast Stochastic Subspace Identification of Densely Instrumented Bridges using Randomized Single Value Decomposition. And the authors are like Elisa Tomasini, Enrique Garcia Macias, and Filippo Ubertini. I wanted to implement and check this article because I think it's quite useful, not in the context of bridges, because to be honest, this paper is not related to bridges. It's actually uh, its focus, or the main focus is on how to improve the SSI algorithm to make it faster, and is agnostic about the structure. I think they mentioned a bridge because they have like a use case of like they test the algorithm in a bridge, but I also think that they have like some kind of grant or something. But this paper mainly focus on, also the value proposition of this paper is like in the improvement of the SSI algorithm. So basically, I will divide this video like in three sections. The first, we will like go through the SSI algorithm. Then we will check the proposed implementation of the randomized version of single value decomposition and why this is faster, and we also like make some uh, live testing of this improved version of the SSI. And in addition, I wanted to like to implement or maybe extend the capabilities, or I think the better way to put it, like to make a real case scenario when this improved version of the SSI really shines. So let's go back here for a moment for the paper. So and basically they first like they make like a literature review, and then they explain the SSI, and then they propose the randomized version of the single value composition, and then they provide that given that now the algorithm is faster, like you as a user can like make more analysis. So now it's possible, well, you can like make a cluster of clusters, but we'll talk about that later. But yeah, basically now that these techniques allows like SSI to be faster, you can like make cluster of the clusters of each results, varying the time lag. And then they make a demonstration using like a 10-story share building. We're actually going to replicate this and also test it ourselves. And then they provide like this equation that I think is the most valuable thing in this paper, this rule of thumb, or this equation to calculate the rank of the tuplets matrix to the reduced or the sampled tuplets matrix. And then like they make like a cute implementation, a comparison, and then they tied this technique with the topic of bridges using like this real world example, and then they draw the conclusions. So well, let's start first with the vanilla implementation of SSI. I will And I will not focus on the theory, only on the implementation part, because this is not like a tutorial or a class or webinar. This is just me like implementing or commenting this paper. So basically, we have to first like divide the SSI algorithm in sections. So the first section is basically to calculate the correlation functions between multiple channels. And then we generate like a blocks for each pair of channels, and then we assemble a Toeplitz matrix with these blocks. And I will explain this better in a second, but this is the general overview. And when we have the Toeplitz matrix, we calculate the single value decomposition of this matrix, and this is the most costly part in terms of computation and memory. And with this single value decomposition, we calculate an observability matrix, then we calculate the states matrix, and then we get the poles, and we identify the Modal parameters of this system. Basically, this is like the sections of the SSIs, and then you have like a stability check when you define some thresholds, and these thresholds are they are like used to identify the stable and unstable modes in frequency, in damping, and if they are like stable overall. So this is like the basic explanation of SSI in simple terms. So let's start now with the implementation. And the first step was to calculate the cross correlation function between the channels. And in this implementation, in my implementation, I'm using the impulse response function because, as you know, I guess, like when you have like a white noise as an excitation, you end up with an excitation with a constant power spectral density. So given that the input is this white noise with constant spectral density, the impulse response function is almost the same as the correlation function. So for this implementation, I'm using natural excitation technique that basically calculates the inverse Fourier transform of the power spectrum between two channels. So you can, if we go to the natural excitation technique, you can see that actually we have here like the channel 1, channel 2. We calculate like the cross power spectrum between these two channels, and then we calculate the impulse response function with the inverse Fourier transform. And this is the same as like correlation function because the input is a white noise basically. So yeah, so you can picture, I'm not going to plot it now, but you can the output of this is like these signals that the graduate students uses to fit random decay or exponential decay models. So basically you have like a delta as an input, and the system like responds. So basically you can imagine that we have like the response, we have like the acceleration values, and we also have like the timestamp. So basically, and this can be long or short depending of the data. Now we are going to connect this with the paper in a second. So after we get this correlation function, or IRF, sorry, between one channel and the other channel for all the channels, we now have to create the topless matrix. And to do so, we first have to make like a block matrix. When we take the correlation function, we put it in the first row, and then in the second we put the same correlation function, but we shift the correlation function to the right. So we basically roll the whole thing to the right, and we do this for all the rows, and basically we end up with a matrix that all the columns, all the diagonals, sorry, are like constant, in the sense that they are, all the values are equal. So if you get, yeah, basically all the diagonals will be like the same, and each row will be um, the same correlation function, but shifted to the right. So that's why each diagonal have like the same element. So let's say, yeah, I think it's clear. And then we create the topless matrix with 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 a group of these blocks. So basically we place these blocks in a super matrix, and then we have like this big matrix that we will use to create we will use to for the for the for to create the observability matrix and the states. Sorry. So here you can see like the implementation of the log tuplets. Basically, actually it's here. Basically, in terms of, this is like how is this is the implementation of what I just yeah, this is basically the implementation in code of the tuplets matrix. And as you can see here, we have like the single value decomposition. So basically this part of the code is the one that takes the most, like require most of the resources, and is quite costly in terms of memory and computer power. And also, like, the main thing is that this matrix T1 is quite big, because it's like a blocks of big matrices. So it's quite big, and it's difficult to operate with. So this paper, let me go back here, sorry, it's this one. So yeah, let me go back to the section. So basically we already went through all the main section of the SSI algorithm, and we are actually in this part. So this paper proposed use this randomized version of the single value decomposition instead of this operation here. They are proposing, and this is like a well-documented technique. This is nothing like unique. It's novel in the sense that it is used in the structural health monitoring like domain, but it's widely used in other like disciplines. So basically, we are going to, and also, actually I have like the implementation here in Python. So let me go through the implementation. So those are like the steps that are required to implement this technique. So basically, first you have to sample the big matrix to create a low dimensional version of this matrix, and is random because you don't want to make like to include bias into this process. So you like make like a random sample out of the big matrix, and then we this super mathematical, so I will not get to it, but basically you are going to compress the 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 doublets matrix, so you will make it smaller using this technique, and this will improve drastically the computation time. But the but it's not trivial the rate or how big the compression will be. So this technique uses this variable that is the rank. So this rank is, you can see it like a percentage of the full size of the doublets matrix. And if this rank is closest to the size, it will be like identical to the to the to the to the original matrix. And if this number is low, you will get like bad estimates of the modal parameters when you are using these eigenvalues for the single values composition of this matrix for creating the observability and calculating the poles. So this is not like trivial. So I think the paper nailed this by proposing this equation. Let me go through this equation. So they say that you can define this value k using this equation, and this equation depends on the size of the doublets matrix. So this k allow you to make it like automatic. Actually, no, this equation allows you to calculate automatic this value k based on the size of the matrix. So if we go here to the new implementation of the doublets matrix, I have the factor here. So this is basically the implementation in Python of this equation. And this function here just is the equivalent of this table that they show here, this algorithm. So yeah, basically this is like the core of this paper. And yeah, after this you calculate this the observability, the states, and the poles, and then you check the stability. So it's like the usual SSI, but we have to now test it to check how fast it gets if we implement this randomized version. So this is the first part of the video. Now let's proceed to the second one. All right. Sorry for the noise. There is a lot of construction around here, so apologies. So well, let's continue now with creating this data. Basically, they use this 10-story share building to generate this data, and these are like the frequency of the modes of the share building. So basically we will replicate this and we will use our version of the SSI and the proposed implementation to compare both. So yeah, let's start. I will not go into the details because I assume that the people watching this video already know how to generate these data. Although I think it will be good if I show the results. So basically, we need to create the mass, the stiffness, and damping matrix. Actually, the damping is constant, and we use Rayleigh to assign like 1% to the first modes, and we increase that value for higher modes. And in the paper, they use like 100 kilograms and 5,000 kilonewton meter. Sorry. So, and they use like 300 seconds of data. So yeah, we are using like 300 seconds of data, and also we are using the same mass that I think is 100 kilograms and the same 5,000 kilonewton meters. The dampings, they are using Rayleigh as well as us. And yeah, basically, well, the only difference will be like the energy, because I'm not sure which uh, what was like the spectral density of the white noise for this, and the noise, I think they do not add noise here. I don't know, like it doesn't matter, we only want like the same data to compare. And also they I don't know if they use how many NFFT points, and if they use like an average or windowing function for generate this PSD, but that only will affect like the energy. The frequencies and the mode shapes and the damping ratio should be like the same in our implementation. So let's go. Yeah, basically this code generates the acceleration, but let's make like a live demo here, a live coding session to plot the accelerations and the PSD. Hopefully we will not make many mistakes, and I will try to explain, talk in English, and also code at the same time without making any errors. So yeah, let me put it here. Let's sync this a bit, like the size. Perfect. So let's start like if name is equal to main, and now we have to call this function main and output the acceleration and the sampling frequency. So ACC and FS will be the output of main. Main doesn't have arguments, and in order to plot it, actually I want to stack vertically in a columns size way this matrix, because this matrix have like 10 acceleration outputs. I wanted to be like columns, so that's why I'm taking the transpose of this array here. And of course we have to import some things. So first let's import matplotlib pyplot as plt. Also we need something to plot the PSD, right? So we can use Welsh, or actually let's use periodogram from, we already have it. Actually we already have these imports, plt and periodogram, right? Perfect. So now we can like iterate over the acceleration columns, so we can create a list of results like PSD results, and we'll use periodogram. The input will be the acceleration for the first column. I is not defined, will be defined it shortly. Also, yeah, basically we can also add like a window and use something like Hamming or something like that, but we will not do it here. But yeah, let's iterate over I in range ACC that shape 1. Yeah, I think this will work. If not, we'll have to debug it. And then let's plot. We can also make like a list. So plt semilog y, instead of like they are using like decibels, but I will use like semilog y. It's like the same, because we don't care about the units of the y-axis. So here we have to plot the frag and the energy. For frag and energy in PSD results, but also we can act like legend. So let's enumerate. So we can like add some, well, now this will be like a double, right? And this will be like an index. And here we could like label, yeah, label. Now channel, we increase, you increase the index by 1. And now we should add PLT legend, PLT show, and if everything goes well, we should see our nice PSD. So let's run the share building code. And this takes like a bit of seconds because like I have like the OBS recording this. So actually you can already see like I have already like some cores being used for the recording. So it's kind of weird in terms of the execution time. So anyway, we already have here the acceleration, the PSD, and you can see like we have like a pointy PSD or belt at the beginning because the damping radius are like smaller and they get bigger and horizontal and fat at the end here. And actually we can like get rid of the zero frequency, make this, and now we can like compare, and actually the units are like hertz and this is energy, but we don't care, like really don't care about energy. And we have some vibration modes here at 5.3, 15, 26, and 35. So for example, this one should be 15. Actually, we can like zoom in a bit here. This 15.8. Yeah, it's about right. And also here we have like, it should be like 5.34. So let's zoom in here. Yeah, it's kind of right. And yeah, the damping ratios are also consistent because it's clear that these modes here have like a big damping ratio because they are like less pointy. So yeah, basically we will test both of the codes using like this data. So let's start with the third section. Yeah, but in this section we need to consider the effect of the OBS of the recordings on the calculation time, because it's not the same like making the test without or with the processor, with the recordings in the background. So you can see like, I have all the cores working and it's not like, yeah, but anyway, let's try to make the comparison as objective as possible. But yeah, because the first approach, like leverage or the way, or like the implementation, like leverage all the resources available. So, and the other one doesn't require like much resources because like uses like a smaller version of the matrix. So it's kind of like not like a fair comparison, but let's try to do our best. Maybe I just stop the recording prior to the execution of the functions, just to have like a better comparisons. But yeah, basically what we will do is that we will compare this implementation, the randomized SVD version, with the vanilla version. Yeah, also I have a GPU version, but in this computer I don't have like a physical GPU. I have like the Apple Silicon GPUs, but it's not the same. So yeah, basically this code, in this code we define like the normal parameters of the SSI. As you can see, we are going to input the data from our main data generator from here, and we are going to transpose our acceleration array, and we will use these two model orders. Like, I think for comparison it's the same. I think I don't know what they use. 0, I'm sorry, it's the same. Like, this don't matter. And the lag they use like 1 to 2.5, sorry, 1.5 to 2.5. But for comparison I want to use like a big value to also highlight some things about this first vibration mode, because as you can see here, with a time lag of 2.5, you identify like this vibration mode. But the problem is that if you increase this time lag, you add more noise into the system, and also the first vibration modes, the lower ones, like, they lose a lot of resolution. And that's why the authors, they suggest that it is important to not only make a single calculation of the model parameters under a set of inputs like model order and time lag. So they recommend to calculate multiple time lags as shown in this picture. Like, each of these points represent horizontally like a run of the SSI, and then they make so each slice in the time lag axis represents like a run of the SSI, and that's the cluster result. Like, this is not the cluster, but it's like the elements of the cluster. And they suggest that you first generate these values, and then you generate another cluster, so like a cluster of cluster. And that's like the main thing about this section of the paper. So first, let's just like a small value first. Let's just like 0.5. Yeah, let's try the code. This patch SSI, and this is with the vanilla version with a small time lag, so this should be faster. As you can see, the output of this version, and we get like the elapsed time of the for, and this value here is the single value decomposition time. So this version took 0.06 seconds to execute the single value decomposition with the vanilla version. But this is like this is not like a normal like time lag. And as you can see here, we have like a good resolution in the first vibration mode. But now let's increase this up to 5. And now I will stop the recording in order to free some processing power in my computer, and we will check the results and the execution and how long it took to execute the whole code. So I will stop now, and we will run the cool. Like, we got our results, and as you can see here, well, let me reduce the size of this. So as you can see here, we couldn't identify the first vibration mode because we the, the we we increased too much the lag time, and yeah, that's why it's important to uh, make multiple runs of this algorithm with different time lags. And let's check the execution time. It took a lot, like 65 seconds took the calculation of the single value decomposition. So now we will first, let's close this. Remember, 65 seconds. So now we will use the version with the randomized single value decomposition. And note how beautiful this API is, like, well, the implementation is that I just have to uncomment one class of the SSI and put the other, and I don't have to change anything else in the code. So that's why this modification of this technique is quite useful, because it's backwards compatible with your monitoring system, and as we are going to see, is quite better. So yeah, let's now go back here to our terminal. Let's clean this. Remember the previous one was like 65 seconds, and in this iteration we will see the actually rank that we are using. Like, well, not the rank, because the rank is defined like as a percentage of the topless matrix, but we will see like the compression of the well, actually the rank in terms of in nominal terms, not in percentage. So yeah, I will stop the recording, I will run the code, and we will check the results. Nice, we have here our results, and as you can see, the results are quite similar to the previous run. We still were able to identify the first vibration mode, and yeah, I will close this, and you can see here that the execution time was 2.9 seconds. We went from 65 seconds to 2.9 seconds. So this is like beautiful. And the most important thing is that we are freeing a lot of memory, so we can run this in parallel in edge devices. So yeah, and also we can play with threads and async functions to maybe receive one acceleration signal and non-block the main threads. So we calculate like the modal parameters in one thread using low resources, and we have like more threads available to take more tasks, like cleaning, preprocessing, reading from database, saving to database, or perhaps like making or having like multiple workers taking chunks of acceleration at the same time. So basically we can even run this technique in parallel, like improving more the gains in efficiency. So that's what I want to to do now, to make this to work in parallel. Because if you check, let me split my terminal, we see like the 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 consumption of CPU usage. I will run this with OBS like recording, and it will be like a bit slow, not much, but you will see that not all the processors are being used. So let's run this, and note that for example, these two are like 0%, 1%. It already finished, but none of the available processors like got like 100% like usage. So because like the memory and also the memory, we have like a we have like a free space to place multiple to store in memory multiple matrices. So this will allow us to to make the calculation faster. I know that we are using this with a time lag of 5 in the paper. They used to, but to be honest, I if the SSI is well implemented short um, for short like small sizes of the doublets matrix, there is no big difference. The magic relies in the in the in the reduction in the memory, because you now can run these multiple times. So yeah, for demonstration purpose, let's change this time lag to, I think that they use 2. Let's use 1.5. And also here you can like I'm using this part is not important now because we are focusing on the comparison, but I'm like generating 10 clusters and we're grouping all the stable poles in 10 but this value is arbitrary. You can make like a clever ways to identify the optimal number of clusters automatically and more efficiently, but it's not the topic at hand. So let's just run this with 2 seconds time lag, and you will see that now we will be only one core is working like at 60%, 84%. So, and note that I have multiple cores available, so I can, if my memory if my memory is not an issue, I can run this in parallel. And let's say that if I have like a queue or acceleration signals that needs to be processed, like I can use like 4 workers to make this process like 4 times faster. And obviously, like if I have like a small queue, the comparison between a sequential execution and a parallel execution is not that big. But if I have like a long queue, like the gains are like 10x the sequential one. So here you can see that we have our nice stable poles, and with short time lag we are able to identify the first vibration mode, which is nice. So now let's have another live calling session and we are going to create, we will replicate this. Like basically we will have like a list of time lags, and we will iterate over the list sequentially. Let me drink some water first before calling. All right, so let's go. So now we have to create a function. This function will be named like Modal ID, and the input will be the acceleration, the sample frequency, and the time lag, so ds. I'm not using any type hints here, so let's keep it simple. So I can take basically this part here, and we can move it up, and now should delete this, and also we can comment this line because we are not going to plot the stability diagram. And now we can like we can create like a list, like ds list, and this list will be like 0.5, 0.8, 1, 1.2, 1.5, 1.8, 2, 2.1, 2.2, 2.3, 2.4, 3, 3.2, 4. I think this is enough. Let me format the code. This is better. And yeah, basically now we have to make a loop. So results will be modal ID. The inputs will be the duration, sample frequency, the TS. Now for TS in TS list, we'll iterate over the list, and we will append all the results here. And yeah, we will use like the clock of my terminal to keep track of the execution time. So let's save this. And now, and I think everything is correct. This is like a variable clusters. Yeah, perfect. So now let's run this. And yeah, you will see that most of the available cores will not reach like 100%. And let's check how much time we will this will take. Note that we are executing this is quite fast, but it still is like sequential. So each iteration will take more time because we are increasing the time lag. So yeah, let's wait for the results, and note that the consumption of the CPU usage is not that high. Actually, we finished in 29 seconds, which this is good. And you can imagine this like in a real application when you have like, let's say, an hour of data. You can split these hours data in multiple chunks of data and process this data in a queue. If you you can split it in 10 chunks and calculate the model parameters in these 10 chunks, and for each of them you can calculate the model parameters with different time lags. So the applications of the advantage of having less memory in the matrix are quite useful in the real world, more than just like a cool paper. So this took 29 seconds, and now we are going to make this process like in parallel. Will a pool of processors. So let's try to code this again in live. So now we have to import from concurrent features, import what's the name of process pool executor, right? So now we have to create like a context manager. Let me comment this, and let's name this like sequential execution. Now we're gonna implement the parallel. And so now we have to create first like a context manager to manage the pool of processes. So process pool executor, we have to call it and name it like pool. And now we have to iterate. We'll create some task in plural, and this will be like a list of tasks. So basically, for each process we will submit the modal ID callable. We will add the acceleration, we will add the sample frequency, and we will add the time lag, and we just iterate over the list of time lags. And also now we have to get back the result as soon as we receive them, so we have to also import here like as accepted, as completed, sorry. So now we loop over the completed tasks, so like for task in as completed tasks, we just like get result equal to task that complete that result, I guess. Yeah, result. And like result, we can like just append this, oh sorry, we have to call the first the list, and then just results, append result. Actually, I can just append in the previous line, but I think this is all right. So now, and remember that this 29 seconds also includes the generation time, that is roughly 10 seconds. But now I will like run it first without recording in OBS, because this approach leverage a lot of free space, leverage free CPU space or free process space, and yeah, the result should be like higher. So I will stop the recording, run this code, and show you the results. And remember that the previous one took 29 seconds. So let's save this and let's check the results. All right, we have our results back, and as you can see, the execution time was 18 seconds. It was like pretty fast, 18 seconds. So now we are like leveraging all the processing power of our computer. So the previous one was 29, now it's 28. So as you can see, now that the matrix are not that big, now our limit is the RAM instead of like, yeah, the execution time and the RAM. Now we can, if we can fit multiple tasks that don't surpass the available memory, we can run it in parallel. So this is super nice for real world application. Like in the past, I will not talk in this video about my past experience working with real monitoring system and making the backend for these systems, but this is like a really good feature to have. Although I have to say that SSI is not the right tool for speed or memory size. There's Bayesian approaches way better than SSI, but they lack like popularity, and people don't know how to integrate that a paper and value and really like identify the value in these Bayesian techniques. But I will try in this video to show the people that for real world application, the Bayesian approaches are the best. But for now, this is good because everyone, like most of the people, only know how to use SSI because it's the most common. And yeah, so basically I will show you how this looks with all the processing, with this view. Like you will see that now each CPU will reach 100%. Hopefully the recording will not stop, and it will take more than 18 seconds because like this approach scales well with more compute. So, and this is important for real world applications, in particular in edge devices. So yeah, let's run it here with the visualization. So first, you will notice like only one thread will generate the data, and now all the magic happened. You can see 100% with 100% with 100%, and I only have like 200 megabytes of memory available. So I think there is some overhead there, but note that still we got like 22 seconds. The previous one was 18, and I don't remember the first run, but it was like more than that. So if you have more cores and more processing power, this scales pretty well. And yeah, I think they showcase like and also a final note. This was super easy to implement here, and imagine this is running AWS or something similar, that you are like in a winning position in terms of your backend. This will be more efficient because you can now orchestrate like a queue of tasks and make async calls and run these in one single thread using low resources. Or if you are like processing like, I don't know, 200 or a year of data, you now can run like in parallel you can process multiple data in parallel, meaning that you will have like 3 weekends and more time for yourself instead of waiting for the code to finish. And yeah, basically this is like the final part of the demonstration, and the code will be available. Like as you can see here, I need to clean a bit these classes because yeah, there are not like I type hints and make like the documentation. In my GitHub repository you have like a version of the SSI. Also note that this is not like a peer preview implementation of SSI. I personally don't use it because, as I told you earlier, like I use like patient approaches because they are way superior than these low-end techniques in time domain. Because this, let's face it, like you are taking like the whole for now. If let's say you are like analyzing like, I don't know, like uh, a telecommunication tower, you only care like for three vibration modes. And with Bayesian approaches, you can also first calculate uncertainty in a better way than any variation that calculates uncertainty of the SSI. Also, you can narrow the scope of your SIF identification. You can narrow the scope of the identification by selecting the range of frequency that you want, and also it's lightning fast, and you can like analyze each mode in one thread. And yeah, I will show this in future videos, so stay tuned. But basically this is like improved version of the SSI, and as I was saying, like perhaps I have some mistakes. If you check the GitHub repository, it can like have some errors especially in the matrix dimension, because it's hard to debug that. Especially I'm not a mathematician, I'm just like a backend engineer, so I just work with real world problems, not like matrices. And and so if anyone find any error in the SSI code, you can make a pull request or add a issue, and I will be happy to keep improving this code. And I think it's important for the community in serial monitoring to have like a lot of open source code available like this. And yeah, basically as a final note on this paper, I think it's quite valuable. Sorry. I think, and why? That's important, because you can like comment on a paper based on your feelings, because there is something useful here, that is the way the reduction in memory and size of the doublets matrix. And also I think is spot on the commentary of making a cluster of cluster. I didn't display like the 3D representation like we are like seeing in the paper, but I think that's spot on. But although you have to calculate also how you have to calculate the uncertainty of each model parameter, because otherwise it will be like useless like this table. And they focus this on bridges, but as I said, this paper only focus, the value is only provided in terms of the in the techniques. So this is agnostic of the structure. It's true that, of course, if you have like a densely instrumented asset, that's true, this helps a lot. And but also if you have like a long time series, or you have like a rigid modes where you need like a bigger time lag. But yeah, like I miss in this paper the compart, because this paper should be focused on the techniques. So how this improved version of the SSI like relates to other implementations or of different identification techniques, like for example the variations, like the frequency enhance frequency domain decomposition, sorry, and next ERA. Like there are like a lot of techniques that should be like compared here, because at the end you can be optimizing the wrong tool for the job. Like the reasons that SSI is the most popular thing, I think, is not only because it's the best tool for identify model parameters. It's a popularity thing. So I think it should be like this work, although it's fantastic, it would be better if they add like a comparison with other techniques, and also focus in the implementation, because you can, if you have like a bad implemented version of SSI, still it will be like slow. Like when you are talking about techniques, the implementation of the technique is more important than the actual technique. So yeah, you can like create like one threaded version of SSI, and you can include the randomized version of the single value decomposition, but still you will end up like as something that underperforms against a well-written version of the SSI, and also comparing it with GPU. So there is a lot of things that you can compare here, but I know that they have to, maybe they have like a grant about bridges, so they wanted to showcase the data of this bridge, which is like super common. This is not like novel. This is basically like a kitsch, and yeah, but it's a good piece of work, and yeah, hopefully I will have some time to clean the code and upload it to the GitHub repository. And yeah, and I think I will record some videos about structural monitoring to make some order in this discipline, and showcase like a real world application more than like just like a nice papers. So anyway, thanks for watching, and see you next time.